This video is about induced electromotive force or induced EMF. We'll start by learning how a current is induced and then move on to discuss how to use Fleming's right-hand rule for induction effects. Let's see how a current is induced. Recall from subtopic 5.4 that when charge moves in a magnetic field, it experiences a force due to the field. The idea of an induced current is closely related to this concept. Induced current is defined as the production of a current in a conductor due to a relative change between the conductor and a magnetic field. By relative change, we often mean relative motion. So, for example, a conductor that moves in a magnetic field. Other examples of changes are changes in magnetic field strength or magnetic field direction. Later in this subtopic, we'll learn about magnetic flux and magnetic flux density. Both of these quantities are connected to induced current and induced EMF. Next, let's see an example of how induced current is produced. Let's assume that we have a magnetic field that is pointing out of the page or screen. A conducting metal rod is moving in this magnetic field horizontally to the right. The rod is moving at a constant speed. Let's apply Fleming's left-hand rule that we learned in subtopic 5.4. The rod contains positively and negatively charged particles. For now, let's focus on what happens to a positively charged particle as the rod moves through the magnetic field. Since the positive charge together with the rod is moving to the right, the direction of the conventional current is to the right, so when we are using Fleming's left-hand rule, our middle finger should be pointing to the right. The field direction is out of the page or screen, so our index finger should be pointing out of the page. If you got the direction of these two fingers correctly, you will see that your thumb is pointing downwards. Therefore, the force due to the field that acts on the positive charge is pointing downwards. Since the direction of the electromagnetic force that acts on a positive charge is downwards, the direction of the electromagnetic force that acts on negative charge is upwards. As a result, electrons in the rod flow upwards, so the direction of the conventional current is downwards. The current that is produced in the rod this way is called induced current. It is induced by the relative change between the rod and the magnetic field. You might be wondering, how can there be a current in the rod when it is just a piece of metal and it is not part of a closed circuit? An important concept here is that a current is induced in the rod even though the rod is not part of a closed circuit. What eventually would happen is that negative charge would accumulate at one end of the rod, while positive charge would accumulate at the other end. As a result, after some time, charge would stop moving. So in order to induce a continuous current, the conductor must be part of a closed loop. Of course, when the current is induced, electrons gain energy, so energy transfer takes place. Some form of energy is transferred into the electrical energy of the electrons. Since energy is transferred into electrical energy, we say that an EMF or electromotive force is induced in the conductor. Keep in mind that in spite of what its name suggests, electromotive force is not a force, but it is the electrical energy per unit charge that is transferred to the electrons, and it is measured in volts. Through our example of the moving rod, we have seen how Fleming's left-hand rule can be used to find the direction of the induced current. Fleming also has a right-hand rule that can be used in this situation to determine the direction of the induced current. Let's see how this rule works. Logically, for this rule, we'll use our right hand. Our thumb will point in the direction of the conductor's motion. our index finger in the direction of the magnetic field, and our middle finger will show the direction of the induced conventional current. Let's go back to the moving rod in the magnetic field from our previous example and use Fleming's right-hand rule to find the direction of the induced conventional current. Position your right hand so that your thumb is pointing in the direction of the conductor's motion, so to the right. Your index finger should point in the field direction, so out of the page or screen, and if you have done this correctly, your middle finger should point downwards, showing you the direction of the induced conventional current. This is the same direction that we found using Fleming's left-hand rule in the previous video. So when you work with the induced current, you can use either of these rules to work out directions. Let's summarize what we have learned in this video. We began by discussing induced current and defined the meaning of this term. Then we examined a metal rod moving through a magnetic field and explained step by step how a current is induced in the rod. We added that during the induction process, energy transfer takes place, so we say that an EMF is induced in the conductor. In the second part of the video, we learned about Fleming's right-hand rule, which we can use to find the direction of the induced current. When using this rule, we should point our thumb in the direction of the conductor's motion, align our index finger with the field direction, and if we do this correctly, our middle finger will show the direction of the induced conventional current. We concluded that when working with induced current, we can use either Fleming's left-hand or right-hand rule. This completes our discussion of induced electromotive force or induced EMF. In the next video, we'll learn about Lenz's law.